Okay, welcome back Physics 20s. This is 1.9 talking about graphing. This is the second video talking about graphing, and today we're going to be talking about accelerated motion. Okay, so we're back looking at graphs, and we're going to start again initially by looking at a position versus time graph, or what's called a D versus T graph. Remember from the last video that the slope of this graph was equal to velocity, but now that we're looking at accelerated motion, that means that the velocity is going to be changing. That's the definition of acceleration, changing velocity. So if the velocity is going to be changing, that means the slope is going to be changing, which means we are going to have a curve. So we get a curve going up like this, which is going to be acceleration or speeding up, or we could get a slope looking like this, which is curving downwards, which is deceleration or acceleration in the negative direction. Now, when we have a curve like this on a position versus time graph, it can ask you for two things. It can either be talking about the instantaneous velocity, which means the slope at a certain point on that curve, or it can be talking about the average velocity, which is a line for the slope from the start of that motion to the end of that motion. So I put some points here in white to show if we're trying to look at the instantaneous velocity at those points, what the slope would look like there. So you just draw a line that would be tangent to that line, or tangent to that curve right at that point. So we see a slope for instantaneous velocity would look like this right there, look like that right there, and look like that right there. For the decreasing one, we have a slope like this. This actually shows that initially the slope is positive. So this is a positive velocity initially. Then we see this one's completely flat, which represents stopped. And this one's going downwards, which represent a negative velocity. So it goes from forwards, stopped, to then going backwards as the slope is representing the velocity at those points. And you can also look at the average velocity. I'm going to show that in yellow here, where you take from the start to the end and draw a line to represent that motion. So this line, we can find the slope with our rise divided by our run, and it gives us the average of that whole time. So if we compare these to the white lines, the white one here is more flat than the yellow line, so it starts off going slower than its average. This one's pretty close to the same, I think, and then this one's faster. So you see the instantaneous velocities are changing, speeding up, but then that yellow one shows the average for the whole time, which looks at the total change in position or displacement over the total time, which is the formula that we used for calculating average velocity, was V is equal to our D over our T, looking for the entire time period. We can do this for the red one as well, looking like that. So the average there would be a negative slope or a negative velocity, which makes sense because from where it starts to where it ends, it actually moves down. So the position moves backwards or in the negative direction. Now looking at velocity versus time graphs, remember from last lesson that the area under the curve represents the displacement, and that still is true when we're looking at accelerated motion. But what we're going to calculate now that we have acceleration is that the slope here is equal to the acceleration. Talked about in the last video, now we're going to have cases where you actually have to calculate that because there is an acceleration. However, it's good to remember that these will all be straight lines on a velocity versus time graph. We're not going to have curves because a curve, remember, would be changing slope. And since the slope's an acceleration, that would mean we're having a changing acceleration. This course is always constant acceleration, so all of these V versus T graphs will be straight lines. They're now just going to be up or down. So from last video, we could have one like this. Now the slope of that, the rise over run, gives us our acceleration. So that's a velocity is going up. So that's accelerated motion. We would find the displacement by finding the area under the curve there. This would be a decelerating because it's a negative slope. It looks like it starts at a high velocity, so it's going forward. When it hits here, that's a velocity of 0. So right there, it's stopped. And then it goes to a negative velocity. So it's going forward, stops, and then goes backwards. And again, as we said in the last video, take the area here, consider that forward displacement, take the area here and consider that negative displacement, as this part is all forwards and this part is all backwards. So we take positive here, subtract this to figure out your displacement from where you started. Now it's good to look at how accelerated motion is graphed on D versus T, V versus T, and A versus T. If we have a D versus T graph like this, it might ask you what it's going to look like on the other two graphs or vice versa. So what we have to look at and really remember is slope and what that equals. So the slope for D versus T is equal to velocity. So the slope of this is going to get put onto that graph. So we look at the slope right here and it's pretty low. right? So that means it's not going very fast. It's not zero. So that means we're gonna start just above zero, but we're gonna start at a low velocity. Then it starts to speed up as we increase here. The velocity starts getting steeper, so we should see that the arrow is going to be going up like this. And you might think, well, do I curve it or do I just draw a straight line? Remember that we're always gonna have straight lines on a v versus t graph because we're only looking at constant acceleration. So I see, well, the velocity is going up, then I need to put a line that shows the velocity going up. And so that would look like this, showing accelerated motion on v versus t. And lastly, we have to know that the slope on our v versus t graph is equal to acceleration. So again, we put the slope onto that graph. The slope here is consistent. It's a straight line the whole time. So that means we're gonna have an acceleration as a straight line across, right? Because this acceleration is staying the same. It looks like a positive slope, and we don't have any values here to calculate it, but maybe it's a slope of something like 2, which means it would be 2 meters per second. So we put a line and just draw it straight across at something like 2 meters per second squared, right? So the slope of this, you calculate it, plot it there, it starts there and continues there the whole time. Acceleration stays the same. Let's look at a little bit more complicated one. Maybe we have motion like this. So it starts off at kind of a high displacement, curves up, and then curves back down. How we plot that on the velocity versus time? Well, it looks like it's going forwards here, stops, and then goes backwards. So we're gonna put that like this. It's at a positive velocity, goes to stopped, and then goes backwards. Again, it's a straight line because our acceleration is consistent. This is a negative slope representing a deceleration or acceleration in the negative direction. So it's gonna be down here in the negative part for acceleration. So let's take a look at an example here. Right now it says determine the displacement and acceleration from the graph below. This is a v versus t graph. Remember, we can find out both of those things, acceleration and displacement. Our acceleration is going to be from the slope, so I need to take my rise over my run. Now it's nice that this is a straight line. It looks like we start at 10 and we finish at, I think this is 35 right here. So I'm going to draw my run and my rise. This is 35 for my rise, and my run is 0 to 0.8. So when I take that, it's 35 divided by 0.8. I mean, that's kilometers per hour divided by hours. I'm gonna get kilometers per hour squared here, which is not a common unit for our acceleration, but let's see what we get. I'm getting 43.75 kilometers per hour squared. Now you might think, well, you can just convert that to meters per second with dividing by 3.6. Because we're looking at a different unit now, it's actually not just divided by 3.6. We have to do that to our kilometers per hour first. So maybe let's do that. 35 divided by 3.6 gives us 9.72 repeating for our meters per second. Now we have to divide that by seconds. So we have 0.8 hours. We would times that by 60 to get to minutes, 60 again to get to seconds. You get a lot of seconds, 2,880 seconds. So let's divide those two and you get a really small number, 0.003376 meters per second squared. So this is a super slow acceleration. Yeah, it might be best if I had one that was accelerating faster for an example, but at least that shows you the concepts for how to calculate it. Now, just before we wrap up this video, you could get a question where you're looking at a position versus time graph and you have a curve, but it's asking you to find an instantaneous velocity. So this says, what's the velocity at 0.4 hours in this case? I think, well, how do I figure that out? Well, remember that on a position versus time graph, the slope is equal to the velocity. So I said, what's the velocity at this point? Well, we're gonna have to look at, say, that's this point on the graph, and we need the slope right there. Now it's changing, so we can't just take like the start of here to the end of here. That would be the average. I want to find what the slope is right at that point. So how you're going to do that is you're going to do kind of like I showed before, draw a line tangent to the curve, which means it's just touching that curve. So it's best to use a ruler for this. I don't really have a ruler on the screen here, but it's going to look kind of like this. Okay, kind of like that. That's actually pretty straight. And what I mean by tangent is just touching this line. You know, like it's a distance from here and a distance from here. The only point that is making contact with that curve is right there. That'd be a tangent line. So now I need to calculate the slope of that line. So how I like to do this is you find a place where the grid or the graph crosses nicely. Like we wouldn't want this point, actually it's pointing to right here. That's kind of like halfway in between. we want to be as accurate as possible. So we want it so it hits like kind of like a crosshairs as good as possible. And I think I see that it does kind of right here, that it hits that point quite well. And I can read this value and I can read this value well. And then another spot is actually right at the bottom here. I think it crosses there pretty well. And I know this is 0, and I know that's right on 0.2. So I'm gonna take my rise over my run. So my rise is 40 minus 0. That worked out well. And my run here, this is 0.6 and 0.8. Now it might be tricky to figure out what that is, but consider this is going 5, 1, 2, 3, 4, 5 across. So if this was only going up 1, say 0.6 to 0.7, each one of those would be 0.2. But now it's going up by not 1, it's going up by 2, 0.6 to 0.8. So that would have to double. It'd have to be 0.4 per square, and I have 2 squares, so it's 0.8. That makes this 6.8 for my first value, and then minus my other value, which is right on at 0.2. Sorry, 0.68 minus 0.2, which gives us 40 over 0.48. Put that in our calculator, and you'd be getting 83.3 repeating. But again, we actually weren't really using these units here for this example. I just made up a curve. By showing you how you draw a line that is tangent to that point, and then you find the slope of that line to figure out the instantaneous velocity. Again, not the best example, you're gonna have a word question there, but hopefully that shows you the method for how to calculate that. And that's it for this lesson, and that's it for graphing. That's it for the end of chapter 1. So make sure you try those practice questions, ask any questions you have in the lifetime, and I will see you in the next video.